Okay, so let's imagine we have a function. Let's go for a nice quadratic function here. And I, in whatever method I do, want to find the gradient here. So I want to know the gradient at this point. Well, my method in the past for finding gradient of straight lines is if I take 2 points and I join them together with a straight line, I can look at the change in y between the 2 points and divide it by the change in x. And there's nothing different here. So let's say that y equals x squared. So the gradient of this line is the difference in y over the difference in x. So what we're going to do is we're going to call this x-coordinate x and this x-coordinate x plus h. So, well, the difference in y is the y value at x plus h, which we can find by putting x into the x plus h into the equation, minus the y value here, which is just when we put x into the equation. So minus x squared. And then the difference in the x value is x plus h subtract x. Okay. Now if we expand this and simplify, we'll see that the gradient is equal to x squared plus 2hx plus h squared minus x squared all over x plus h minus x, which is h. We can cancel the x squareds, divide by h, and so we are left with the gradient of this line being 2x plus whatever h is. Okay, so that's in general. But this isn't really an accurate depiction of the gradient, because we can see that the steepness of this red line is not the same as the steepness of the blue curve at that point x. So if we take another point x here, and let's say I move my line so that it now goes through there, well, that's a better estimate. And if I take another point here, and I move this so it goes here, again, we're getting closer and closer. Now what we want is we want our second point x plus h to be almost exactly next to x. And so if we look here, if I make this line a little thicker, I'll have shape format. So for example, this, well, maybe that. So here I can see that it's almost exactly on top of the blue line, which is really what I want, because this means that the gradient of this straight line is the same as the gradient of the curve at that point, which is ideal. Now, what can you tell me about the value of h when I compare the 2 points? So the one at x and the one just to the right of x. Do I want h to be big, small? What do I want it to go towards or tend towards? Yeah, exactly. So I want it to be really small. So what we do is we define the first derivative, f dash x, as the limit as h tends to 0 of f of x plus h minus f of x all over h, which is, in other words, the change in y divided by the change in x. And we take it as h goes to 0. Now, the reason we say the limit as h tends to 0 is because we can never really have h being completely 0, because that means that one point is completely on top of the other point, and there is no line joining them up. But what we do is we take then this equation, so the limit as h goes to 0 of 2x plus h, and the rule with doing this is any h terms disappear. So the derivative is 2x, which is what we knew. So in general, for differentiation from first principles, we know what the outcome we expect is. So we know what the outcome should be. We just need to find it. And for the exam, you will have up to cubic functions of x. So while it's technically calculus, the main method will include putting x plus h into whatever the function is, expanding the brackets, subtracting then the original function with just x is in, and dividing it by h. Okay. So no, I don't think I found a question on this from the papers that I've been using, but I do remember in my year it came up as a either 4 or 5 mark question. So if you want a bit of practice, then you can try using first principles to differentiate x cubed plus x. Okay, so have a go at that, and as with everything else where we sort of leave it sort of open-ended, I'll fill in the full solution in a week or so. Nice. So the real meat of this is implicit differentiation. And implicit differentiation is whenever we have, say, we're trying to differentiate an overall equation with functions of the variable. So for example, in terms of x and y, this is an x and y combined equation. Now, typically, we still want to find how y changes with x. So we're still looking for dy by dx. But most of the equations that we will use won't have it written y equals. So it won't say y equals, which is why it's easier to use this implicit method. Now, implicit differentiation is really just an application of the chain rule and sometimes the product rule. So for example, I know that y is equal to f of x. Okay, so it's a function of x. I don't know what that function is. To be honest, in a question like this, probably don't care what that function is. I don't need to know it. But I know that y can be written in terms of x. And let's say I want to differentiate y squared. Well, this is exactly the same as when we have a known function of x. So, for example, it's similar to differentiate x squared plus sine x squared. So what we would do is we would call this u, we differentiate u, and we differentiate the outside function, and we multiply them together. So that's what we're going to do here. So this is exactly the same as the chain rule, just with a slightly different sort of symbols that we're going to be using. So I know that overall, I've got the equation, let's call this, I don't know, z equals y squared. And I know that y is equal to, let's say just y equals f of x. Well, so z dash is equal to 2y, and y dash is equal to f dash x, or we could say dy by dx. So when I multiply these two together, for the chain rule, this tells me that the overall derivative with respect to x, so the overall derivative is equal to 2y times dy by dx. And that would be your final answer for differentiating this. So in general, if we have, so if a symbol is an unknown function of our variable, and here it's nice because it sticks with just y and x. Rates of change is a bit more complicated because we have to be on our toes a bit, making sure we identify when it's a function of our variable. To differentiate, what we're going to do, notice that 2y, well, if I had x squared, it would differentiate to make 2x. So we differentiate normally. And then once we've differentiated it normally, say to get the 2y, we multiply by d, whatever the function is, in this case dy by dx. Okay, so for example, let's say I've got x cubed plus y plus sine y equals 2y. Okay. So differentiating a function of x is still exactly the same. So we have 3x squared. Sine of y is going to become cos of y when we differentiate it normally, or cosy, but then we times it y by dy by dx. 2y, if we differentiated it in this normally, would become 2, and then we multiply it by dy by dx. So if I needed to find dy by dx, by doing this, I've got everything that was a function of y times dy by dx. So we can relatively easily make dy by dx the subject. Whereas it wasn't easy for us to do that previously. So here we'd get dy by dx 2 minus cos y equals 3x squared. Dy by dx equals 3x squared over 2 minus cos y. Okay? And in general, that then is the new method that we have here. A couple of pointers. Equations for implicit differentiation will be made up of a mixture of 3 things. If we just have functions of x, so just, let's just call these x terms on their own. This is as normal. 2, for y terms, we do as above. And if we have any terms which are, say, x, y combined terms, any ideas how we approach any function which may be like x squared multiplied by sine y? What would we do there? So we'd use the chain rule in implicitly differentiating. But so if we had, say, x squared sine y, well, here we would use the product rule. So use the product rule, but in the product rule, we would also have to use the x and y terms as above.
I hope you enjoyed the video. If you did, be sure to click down here to like, subscribe and share with a friend. If you'd like to access the full online course, including the notes pages we were making, there's a link in our description below. Thank you for watching and good luck with your revision.